On the previous tape, we examined the authorized GM diagnostic techniques. But we also mentioned that even if all the procedures were followed properly, we could still end up with a car that had drivability problems. In this tape, we'll teach you how to overcome this obstacle by going over a field-developed diagnostic procedure that has proven effective in service bays across the country. Once you have mastered this procedure, you'll be well on your way to earning a reputation as an expert in diagnosing and correcting 3C problems. Before we begin, let's take a look at some of the special tools you'll need to get the job done. They include the common carburetor float scale and carb float level gauge, the solenoid idle air bleed gauge, the sliding scale, the idle adjustment, and multi-purpose tools and adjusting tools. As we go along, you'll see how using the right tool can save you time and aggravation. Once again, don't forget the importance of a properly running engine. Compression, fuel, and ignition all have to be in good condition before you can make a valid diagnosis of computer-related problems. Another lesson that bears repeating is that if you put faulty data into the computer, you get faulty data out. That's why using our new diagnostic procedure is so important. It filters out faulty data by making sure the data going to the ECM from the individual sensors is correct and the computer is issuing the proper commands. Before beginning this new procedure, there are a couple of things you have to do first. For starters, you need to unhook the EGR and canister purge and unplug the PCV from the crankcase. Next, check to see the ECM is working properly. This involves making sure the computer is in the car with the correct prompt and that the connections are intact. To check the computer function, you ground the computer test terminals and turn on the ignition. You should be able to hear the mixture control solenoid pulsing at 10 times a second. If it's not, take the float scale and push down on the paddle. If you're able to, you know there's an electrical or computer problem. Another MCS check from outside the carburetor is letting it pulse for 3 minutes or more to allow heat and resistance to build up normally. If it stops or there's any interruption in the pulses, this indicates an electrical problem within the mixture control solenoid itself. The next thing you want to check is the throttle position sensor. Like the MCS, it's located inside the carburetor, and you're going to perform what is called a TPS sweep test. For this procedure, you'll need a high impedance digital voltmeter and 3 jumper wires. Our test lead is a factory-made rig that plugs into the TPS at the carburetor and into the computer connection. The sweep test is done by hooking the high impedance voltmeter between the blue and black wires. You connect to blue and black on all GM throttle position sensors. Next, from inside the car, slowly open the throttle by exerting steady pressure on the accelerator. As you press down and open the throttle, the voltage should go up. This increase on the meter must be smooth and gradual. Any sudden surge, either forward or back, indicates a bad spot in the throttle position sensor. For example, because the ECM can only react to the information it receives, a sudden decrease can cause the computer to erroneously call for intermittent locking of the converter clutch, a condition commonly called fish biting. If you do find a surge, even as little as 0.2 of a volt, you'll want to replace the TPS. Now, with the pedal all the way to the floor, the meter reads 4.29 volts. You then go under the hood and open the throttle by hand. What you want to do is compare this reading with the one taken from inside the car to be sure the linkage is operating at full capacity. With manual operation, we get this reading, or a full 0.2 of a volt higher. This tells us we are losing 0.2 of a volt to our linkage. 0.2 of a volt may not seem important, but it is. With a 4-barrel carburetor, a loss of even 0.2 of a volt can result in a reduction of 1/2 of secondary operation. To go one step further, a 4-barrel carburetor needs 4 volts to go into the power enrichment mode, while a 2-barrel needs 3 volts. A shortage of 0.2 of a volt at either of these points can mean serious drivability problems. Assuming the TPS and MCS are working properly, you can now proceed to the next step, removing, calibrating, and reinstalling the carburetor. It is our experience that even carbs with only a few thousand miles on them should be recalibrated. We frequently find that almost new off-the-line equipment is not completely up to spec. The first thing you want to do as you're removing the carburetor is to see if it has an electric heater grid. If it does, thoroughly inspect it for erosion, especially the bottom side. This step is crucial because a badly eroded grid can cause serious problems in the engine if a particle of metal were to fall into it. If the grid does show signs of erosion, it's a good idea to replace it, even though it may be working properly. When the erosion check is completed, you're ready to go to work on the carb itself. We strongly suggest that you have the tools you'll be needing close at hand. And since you'll be working with small parts and delicate mechanisms, it's also a good idea to clear away the debris from the last brake job. The first thing you want to check on the carburetor are the screws holding the throttle plate to the bowl. In the majority of cases, you'll find they're loose and need to be tightened. For purposes of this demonstration, we'll be working with a 1983 Quadrajet carburetor with relatively low mileage, which means it will only require a routine setup and calibration. If this carb had quite a few miles on it, we'd probably have to rebuild it as we went along. To begin the calibration procedure, you remove the hardened steel plugs which protect the fuel mixture screws. The easiest way to do this is to take a center punch and give it a few good taps at just about this point. You don't want to get too far back, or you might damage the mixture control screws. The punch should go through the aluminum base and make a small hole in the plug itself. Next, take a sharp cold chisel and set one corner into the hole. A sharp blow at this angle will cut a small, clean notch in the carb and pop out the lug all at the same time. This quick, simple procedure helps you avoid the possibility of doing serious damage to the carburetor. As you cut the notch, you may find that a portion of the plug stays in the holes, but don't worry about trying to dig them all out. You'll usually find that the adjusting tools will fit anyway. Now that you have access to the mixture screws, you want to see where they're set. This may have been done at the factory or by the last person to work on the car. To check the setting, turn the screw in until it's lightly seated, counting the turns as you go. As you can see, this screw gives 3 turns until it's seated. The other screw gives 3.5. This discrepancy between the number of turns is a sure sign that the carb was not properly balanced. Both mixture screws need to be at the same number of turns for a balanced carb. After noting where the mixture screws were set, you want to remove them completely, check for any damage, and make certain the tapers match. Mixture screws may have a short, fat taper or a long, thin one. Be sure that the screws match. We've found instances where they do not. Assuming the screws are in good shape, you can return them to the carburetor and tighten until they are lightly seated. You then want to set them to factory specs. This information is provided in the shop manual. Setting mixture screws to factory specs is a fairly recent development. In the old days, you might just back them out to 3 turns and balance them with the idle adjustment. But since 1981, it's been necessary to be more cautious because the correct setting may be anywhere from 1.5 to 6 turns. If you're off by even a couple of turns, you could be starting out at either too rich or too lean, and that means trouble right from the beginning. The factory specs for this 1983 carburetor call for 3.5 turns, so you'll need to lightly seat and back out 3.5 turns. Now the carb is balanced, and we're ready to move on to the next step. To remove the cover over the idle air bleed, you take the cold chisel again and knock the heads off the 2 pop rivets holding it in place. You then take the punch and knock the body of the rivet out of the hold. When you do this, Be sure to turn the carb over and shake out any pieces which may have fallen inside. We don't want anything left inside to damage the carb when it's back and running on the engine. Now it's time to turn our attention to the idle air bleed. Just like with the mixture screws, you're going to want to see where it is set. To do this, turn it slowly until it is lightly seated, counting the number of turns as you go. In this case, it was 4.5 turns. Make a note of that for future reference. Then, remove the air bleed completely. The first thing about air bleeds you should be aware of is that the ones used since 1982 have a small letter on them. It's important to know whether there is a letter, and if so, what the letter is, because air bleeds are not interchangeable. On 82 and later types, the carb number is needed to determine the correct air bleed. O-rings on the air bleed are also important. There's a large O-ring toward the top and a smaller O-ring toward the bottom. These O-rings need to be intact in order to assure proper idle adjustment. For this reason, we recommend that the O-rings always be replaced when the bleed is removed. It's also important to note that these are not your standard O-rings. They are metric O-rings. And while you can't find them in your standard O-ring assortment, they do come in carburetor kits or can be purchased in individual packages of 2 rings. And remember, you cannot replace metric O-rings with standard O-rings. They must be of the same type. The next important area of discussion is the throttle position sensor. In order to get to the TPS adjusting screws, you'll have to remove still another plug. To work on this plug, you'll need to get the accelerator pump arm out of the way. This is done by taking the punch and knocking out the roll pin that holds it in place. Before going any further, look for a little green plunger that goes down through the air horn. It operates the throttle position sensor and must be handled very carefully. Damage to the surface of it can cause problems which could result in having to replace the TPS. The easiest way to get the plunger out is to press down on it and let the spring pop it out. Never grip it with the pliers or any other tool. Once this is completed, you're ready to go to work on the plug covering the TPS adjusting screw. While this isn't a difficult procedure, it does take a few tricks of the trade. We have found that the easiest way to remove the plug is by drilling a small hole which measures approximately 7/64. You want the hole to be in the center of the plug, but do not begin by center punching it. This could force the plug in tighter and damage the TPS screw, which is only about 2.5 millimeter hex. After drilling the proper hole, insert a sheet metal screw. Next, attach a slide hammer puller to it, and the plug should come right out. Once the plug is removed, you can go on to dismantle the rest of the carb. When removing the air horn, be careful not to damage the gasket. One safety tip is to use a small straight edge to hold the gasket down on the bowl as the air horn is gently taken off. This not only keeps the gasket in good shape, but should also save you from having to replace it. As the air horn is lifted off, you'll notice this small pin or finger. When it is in place, it touches the TPS and positions it for making necessary adjustments. To prevent damage and aid assembly later, we found it helpful to back out the TPS screw until the pin is flush with the air horn. The next step is to look at the air horn and inspect 2 seals. In most cases, you'll be able to reuse the seals, but if they do need replacement, you'll find new ones in the carb kit. They also must be replaced if the carb is soaked in carburetor cleaner. The function of these plugs is to keep atmospheric air out of the carburetor. One seal is at the accelerator pump plunger entry, and the other seal is for the green TPS plunger, which was taken out earlier. Both seals are extremely important for maintaining a proper air-fuel mixture, and here's why. The air-fuel mixture in the car depends on the air entering the bowl through 2 vents which open into the air cleaner. If you look at the design of the air cleaner, you can easily see that the air intake hole is relatively small. According to the law of physics, As air is drawn through a small opening, the velocity increases and the pressure drops. A drop in pressure is generally noticeable at speeds above 30 miles per hour. Because the carb vents are located inside the air cleaner, all carburetor adjustments are made to compensate for this drop in pressure. And here's where the seals become so important. They're located outside the air cleaner, and if they're missing, they let air in at normal atmospheric pressure, which totally fouls up the air-fuel mixture. That's why the seals must be intact and in place. Before setting the air horn aside, there are two more plugs that need to be removed. They are the lean stop plug and the rich stop plug, which you'll want to save and replace in the carb later. To remove the lean stop plug, you have to take the punch and tap it out. This will give you easy access to the lean stop adjustment screw later on. To get at the rich stop plug, you first need to take the rich stop adjustment screw out of the carburetor using this special tool. You can now get the rich stop plug down inside the carb. After the rich stop plug has been taken out, put the screw back in and tighten it until it just touches the air horn, then back off slightly. Trying to muscle an over-tightened screw could destroy an expensive tool. With the plugs out, you're ready to go on to the bowl of the carburetor. The first thing you want to look at in the bowl is the mixture control solenoid paddle. Even though it was operating correctly in the earlier test, you still need to do a visual inspection by pulling out the paddle and making sure both arms are even. It's also a good idea to take a small straight edge and hold it across the arms to make sure they're parallel. A bent arm will result in uneven positioning of the metering rods. The next thing to look for is pitting on the underside of the paddle arms. On high mileage carbs, this can become a serious problem. A badly pitted arm, one with a small hole worn in it, can cause uneven travel of the metering rod and incorrect fuel delivery. If you discover signs of pitting, the complete mixture control solenoid should be replaced. After making the visual inspection, you're ready to remove the metering rods. Be extremely careful to watch for the fine springs which fit around the rods. They're quite thin and can easily be lost. More importantly, without the springs in place, the rods will just lay in the bottom of the jet and will not be able to do the job they were intended for. As you remove the rods, carefully inspect them for damage or bending. They, of course, must be perfectly straight to operate properly. You'll also find a number and letter on the metering rods, but you'll probably need a magnifying glass to see them. The letter tells you the type, and the number, usually 2 digits, indicates the size. Using a micrometer, measure the size at the second step of the rod. The number and your reading should match. However, we have found cases where 2 different sized rods were used in the same carb. Needless to say, this causes drivability problems. The next step is to remove and visually inspect the solenoid for potential causes of failure, even though it passed our initial test. To do this, you have to first push down on the solenoid plunger. Then remove the lean stop adjustment screw with a special tool. Although the plunger only needs to move 1/8 of an inch, you'll find the spring action is very strong. You must release this pressure before removing the lean stop screw. Here's why. The lean stop screw has a very fine thread of 72.57 threads per inch, and these same threads are cast into the carb itself. If you don't release the pressure on the lean stop screw, there is a good chance of removing the threads from the bowl at the same time you're removing the screw. In most cases, this will mean having to replace the bowl altogether. With the lean stop screw out, you can now remove the mixture control solenoid. You'll be looking for any one or a combination of the following 3 problems. If you find any of them, you should replace the MCS. The first thing to check for is a small hole in the bottom of the solenoid unit. Look inside for small chunks of insulation. In extreme cases, these chunks of insulation may have entered the carburetor and fouled the system. The second place to inspect is the wires in the unit. Here, you'll be looking for insulation oozing around the wires, a very damaging set of circumstances. The last thing you should check for is pinched wires with copper showing. This is a potential source of shorting or voltage loss. Again, if you find any one of these three problems, you must replace the MCS. The next thing that needs to be done is checking the carburetor float weight. This has become necessary because of the increase in alcohol mixed fuels around the country. Factory specs for this particular carb float call for a weight of 7.5 to 8 grams, but you could probably work in a range of 7 to 8 and still be okay. This float weighs in at exactly 7.5, indicating that it's in good shape and can be put back in place. When repositioning the float, make sure to check the float level and then set it to factory specs. This is the basis of correct fuel management in any vehicle. Positioning the float is done by applying just the right amount of pressure to the needle seat assembly. It's made up of very soft material, and if you do push too hard, you'll get too high a setting. On the other hand, you don't want to push too soft, or you'll get too low a setting. It's because of this precarious situation that we recommend this special tool. It has a built-in 6-ounce weight to properly position the float, and is the most efficient way yet to assure an accurate float level. One special service tip we'd like to mention is that if you live in generally hot climates, you'll sometimes want to set the float at 1/32 of an inch under factory specs to help offset hot starting conditions. With the float back in place, you can now put the rest of the carburetor back together and make some critical adjustments. First, put the mixture control solenoid back in place and make sure that you can push down on the solenoid. There's a small pin on the bottom of it which must line up with a small hole in the bowl. When properly aligned, you can push down on the solenoid and it will become properly seated. Next, carefully coat the lean stop screw with a light refrigerant oil and replace it. Then finger tighten it until it is lightly seated and the MCS cannot move. You're now ready to make the final adjustment. Using this gauging tool, slip it down over the main metering jets. Then put your paddle in place and push down. When it is in the down position, back out the lean stop screw until there is clearance between the paddle and the gauge tool. Then, turn the lean stop screw until the paddle just touches the gauge tool. You can now put your metering rods back in place and replace the filler block. Once all this has been completed, you're ready to put the top back on the carburetor by replacing the accelerator pump and tightening the connector screw. The way this is done is by carefully positioning the carb gasket and dropping the MCS paddle in place. This is also the stage where you'll see how removing the throttle position sensor pin earlier can make reassembly easier. The first thing to do is line up the MCS connection and accelerator and hold them in place with your finger. Then take a small straight edge and hold the TPS pin up out of the way and set the top down on the base. When the straight edge is removed, the pin should drop naturally right in place. Only then can you put back all the screws. The next step involves reconnecting the accelerator pump linkage. But first, you need to replace the little green plunger that was set aside earlier. Without it, no change will show up in the throttle position, and the TPS will not be able to function, especially in the power enrichment mode. After all the hardware is reconnected, go on and make the rich stop adjustment. Take the float gauge and insert it to rest on top of the pedal, then push it down. You should be able to read the amount of downward travel by counting the lines on the gauge. Each line is equal to 1/32 of an inch. Pushing down the gauge, we see that it reveals 6 lines or 6/32 of an inch. We want this to be only 4/32, so it's necessary to adjust the rich stop screw until there are only 4 lines of travel. The idle air bleed can now be put back in place. But don't forget that the metric O-rings have already been replaced with new ones, so we'll need to apply a thin coating of light refrigerant oil to the rings. Next, lightly seat the unit by hand and back it out 4.5 turns. Then take this tool, which is especially designed to measure idle air bleed adjustment, and turn the idle air bleed until the tool just touches the top of it. With the exception of the lean and rich stop plugs, you are now through with the carb and can replace it in the car. The reason the plugs are not being replaced at this time is because further adjustments may need to be made after you start working on the engine. That completes this segment of our field-tested diagnostic techniques. We should note that the procedure you have seen here on a quadrajet carb is exactly the same for a dual jet carb. As for vari-jet carbs, the recalibrating procedure is a bit different, but not nearly as complicated because the vari-jet itself is not as sophisticated. By now, you can see clearly that this diagnostic procedure takes a lot of time and effort. But we feel it's well worth the trouble because it allows you to pinpoint and repair drivability problems that the trouble codes failed to detect. In the next segment, we'll discuss the output controls and show you how to bring them up to the level of your newly recalibrated carburetor. Only when all of the 3C components are working together can you maximize engine performance. This tape, we'll be finishing up our discussion of the field-tested diagnostic procedure. The last area we'll be covering is how to make sure all the various components of the 3C system are operating in acceptable ranges. Remember, any improperly functioning sensor can provide the computer with inaccurate information. That's why the ECM can only work as well as the information it gets. It doesn't have the intelligence, not yet anyway, to decide which data is correct and which is false. At the end of the last tape, we had completed the carburetor bench work and calibration, and we're ready to reinstall the carb on the engine. Well, that step has already been taken care of. We're now ready to get into some final checks and adjustments. The first thing we're going to do is make a throttle position sensor adjustment using the digital voltmeter. With the meter hooked up to the TPS, we'll set the TPS voltage to specifications. TPS position specs vary by carburetor. For this car and engine, the specs call for the throttle to be set at the high step of the fast idle cam and have a reading of 0.52 hundredths of a volt. As you can see, we're not quite there yet. To get us closer to the correct voltage, we want to turn the TPS adjustment screw until we hit 0.52 volts. If you're off by 100th or 2, don't worry. We're going to be making a final TPS adjustment later on. The next thing we want to do is a coolant sensor drop test. This is done by first unplugging the coolant sensor from the ECM, then taking a jumper lead and making a connection between the coolant sensor and the ohm meter. Once this is completed, we're ready to measure the resistance in the sensor. On a cold engine, we want a reading of 1500 ohms or higher. And as we start the coolant sensor drop check, what we're looking for is a resistance drop of 200 ohms or more in the first minute after the engine is started and warming up. If there is a drop of 200 ohms in 1 minute, we know the coolant sensor is working properly. Let's see where we are. There, you saw it, a 200 ohm drop in less than a minute, indicating that the coolant sensor is all right. If it had taken longer than a minute for it to drop 200 ohms, we would have removed the coolant sensor and cleaned it with a wire brush to get rid of any impurities it may have collected. Incidentally, the threat of dirt and deposits is why it's so important to have a clean cooling system on today's cars. A poorly maintained cooling system can ruin the coolant sensor. If cleaning the sensor doesn't result in a drop of 200 ohms in 1 minute, it means you'll probably need a new coolant sensor. The next 4 checks must be done while the engine is still cool, or you won't get the answers you're looking for. Answers that can solve a lot of cold drivability problems. While the engine is still in open loop, make sure that the EGR system and canister purge are not engaged and that the EFE is. You should also check to see that the air management system is sending air to the exhaust manifold to warm the oxygen sensor and catalytic converter. These system checks are pretty easy to complete, but remember, the engine must be cool and in open loop. In addition, all you'll need to make these tests is a simple vacuum gauge. To check the EGR, connect the vacuum gauge to the EGR hose and, with the carb at the high step of the cam, start the engine. If the EGR is working properly, you should get no reading on the gauge when the engine is cold. After reconnecting the EGR hose, you can move on to the EFE check. Simply connect the vacuum gauge to the EFE hose, and with the engine running in open loop, you should read vacuum. It is this vacuum that closes the EFE valve. Assuming you read vacuum, reconnect the hose and visually check to see if the valve has changed position. On an engine with a heated grid system, you can check for system voltage at the red wire. To check canister purge, you disconnect the hose and use the vacuum gauge again. With the carb at the high step of the cam, you should see no vacuum. Sound a little complicated? It's not. Just remember that on the canister purge and EGR, you don't want any vacuum reading, and on the EFE, you do. It's that simple. Before going on to check the air management system, make sure all the hoses are properly reconnected and the engine is cool. To make this test, you feel the hoses to determine where the air is going. In open loop, the air will be going to the exhaust. In closed loop, the air goes to the catalytic converter. Since for our tests we're in open loop, you should feel the air going to the exhaust. These tests may seem unimportant, but as we've mentioned before, making them can solve a lot of your customers' cold drivability problems. The next component that needs to be checked is the oxygen sensor. As you may remember from an earlier tape, we suggest the manifold be slightly warm to facilitate the removal of the O2 sensor without damaging it. To make this test, you'll need a digital high-impedance volt-o-meter and a clean-burning propane torch. It's important that you use only propane to prevent damage to the sensor. Starting with a cool sensor, heat it with the torch and watch the meter. You want to see it rise to 0.6 of a volt in the first 15 seconds. Continue to heat the sensor up to 60 seconds and look for a meter reading of 0.8 of a volt. Once again, the key readings are 0.6 of a volt in 15 seconds and 0.8 of a volt in 60 seconds. As soon as you see 0.8 of a volt, remove the sensor from the flame. The meter reading should drop to less than 0.2 of a volt in 4 seconds or less. If you see this kind of drop, you know the sensor is probably working all right. But to be sure, you should repeat the test 3 more times. This is sometimes called exercising the oxygen sensor. And the faster it responds, between 0.8 and 0.2, the better, because this assures a proper air-fuel mix. Just to show you what a weak, faulty sensor reading would look like, we'll try the test with this one here. Keep in mind that O2 sensors can start to get weak after as few as 25,000 miles. It's important to make this test because a sluggish sensor can cause problems. When we heat this faulty sensor, the meter reads 0.6 of a volt in the first 15 seconds. But after the full 60 seconds, it has not risen very much. What's more, when we remove the heat source, the voltage slowly drops. These kinds of responses indicate that the O2 sensor is not working properly, and as a result, the air-fuel mix will not be correct. Incidentally, the car this sensor was taken from showed no stored trouble code to indicate an O2 sensor problem. That's because it was working within the narrow range allowable by the computer. Or in other words, it was working, but not effectively. In order to make the next diagnostic check, we'll need to run the engine until it goes into closed-loop operation. We'll be using the dwell meter or duty cycle meter to check for major fuel control problems in the carburetor. To do this, you have to first disconnect the canister purge system. There are two main types of purge systems, and each uses a different type of canister control valve. The first and more simple purge system uses a single diaphragm operated by manifold vacuum. Here's a cutaway drawing of the valve. This type has a hose from the carb bowl to the control valve and onto the canister. When manifold vacuum is applied to the diaphragm, it pulls the purge valve up and shuts the purge off, preventing the carburetor from venting to the canister. It's only when you open the carburetor and apply ported vacuum or purge vacuum that you can succeed in purging the canister. If this diaphragm were to rupture, the control valve would cease to operate and we'd be sending fuel vapors into the manifold. To prevent this, all you have to do is pinch off and/or disconnect these lines so that no fuel vapors can get into the engine. The second type of canister control valve is more complicated. It has created many problems in the past because it has a tendency to suck fuel out of the carburetor. This type of control valve uses PCV vacuum to purge the canister. And as you can see in the diagram, it has two diaphragms operating the valve assembly. If the lower diaphragm ruptures, the strong PC vacuum will cause raw fuel to be drawn right out of the carburetor. That's why when working with this type of canister control, it's better to remove the canister hose and the PCV vacuum hose, then plug the PCV hose. After having disconnected the canister purge system, we're ready to proceed with the air-fuel ratio check. The EGR is unhooked and plugged, so there won't be any EGR influence while we're making our calibrations. The PCV valve has been taken out of the crankcase and is drawing fresh air, so no fuel-contaminated oil affects the readings. And canister lines are pinched off. We can now start the engine. With the engine running in closed loop, check the dwell meter. You're looking for an operating range of 30 to 70% on the duty cycle scale, or 18 to 42 degrees on the dwell scale. Ideally, you'd want a 50% or 30-degree dwell reading. Looking at the meter, we see we're in the desired operating range. This tells us that the settings we made on the bench are pretty close to where we want them. It also tells us a few other things, that the factory settings we used are close to right on the money, that our metering rods match and are balanced, and that we have a good, tight engine with no air or exhaust leaks. If we were getting a reading of, say, 10% on our duty cycle, the rich command side, we would know that the car's running too lean. However, we could be tricked into a false reading if the air management system was still sending air to the exhaust manifold. That's why it's important to follow each step carefully and accurately. On the other end of the scale, a 70% reading on the duty cycle, the lean command side, indicates the car is running too rich. That means we're feeding too much fuel and need to make some serious adjustments. Because we were well within the desired range, we know we can probably trim adjust the carburetor to arrive at the 30 degrees or 50% readings we need for an ideal 14.7 to 1 air-fuel mixture. Knowing this, we can move on to the timing check. Timing is critical to a 3C engine. Experience has taught us that the best way to check timing is with a magnetic timing device. Lights are just not accurate enough for the critical adjustments we may want to make. Ideally, we'd like to be within just 1 degree either way if possible. The first thing we need to do is unplug the 4-way connector at the distributor. We have to get the computer out of the picture so that we can turn the distributor to set our timing. With the engine running, we look at the advance meter and see that this engine is at about 13.5 degrees. The specs for the engine say it should be at 15 degrees, so we'll need to loosen up the distributor and reset it for 15 degrees. Once the computer is out of the system, we speed up the engine to 2,500 RPMs to see if the timing changes. The meter shows timing did change, which means the HEI has change capability and the timing module is functioning properly. The next thing we want to do is set the fast idle. This is important because the throttle position sensor is adjusted on the high step of the fast idle cam, and we can't get an accurate TPS adjustment without the fast idle being properly adjusted. To do an ISC adjustment, we go to the idle speed control motor, which has 4 connectors, and hook the test lead to terminals C and D, the 2 closest to the motor. Using this tester, we then push on the nose switch and get a red signal light that tells us the ISC throttle contact switch is operating. You could do this test using jumper wires, but it's definitely worth the investment in a factory rig. We found this the most efficient way to get into power balance testing on cars with ISC or fuel-injected cars with idle air motors. With the tester hooked to the C and D terminals, retract the ISC motor plunger until the carburetor linkage comes to rest on the curb idle screw. After checking the manual for idle speed specs on this engine, you'll want to turn the idle screw according to specs to achieve minimum authority setting. Remember, accuracy is very important in making this adjustment. The next step is to extend the ISC motor plunger until you hear a ratcheting sound. Following the book specs again, we turn the plunger to set the maximum authority. It's very important that the minimum and maximum settings be to exact specifications. Improperly set limits can cause a condition known as hunting. Simply put, hunting is a situation where, when stopped at a light, the idle speed varies as the computer searches for either the upper or lower limits of the range. If the ECM can't find either the upper or lower limit, it continues to hunt for it. Needless to say, this is a very annoying driver complaint. We're now ready to make the final air-fuel mixture adjustment. The best way to visualize this adjustment is with what we call our performance window diagram. The top end of the window is full rich, the bottom is full lean. The center of the window is our 14.7-to-1 ratio, which translates into either a 30-degree dwell or 50% duty cycle. Our goal is to operate in the center of the window at both idle and 2,500 RPMs. The size of the window is determined by the travel of the metering rods in the carb. In the first part of this tape, we saw the travel for this carburetor was 4/32 of an inch. That's our whole window. Now try to picture the window being centered inside the carb. To move the entire window while retaining the 4/32 of an inch travel, you must adjust both the lean and rich stop screws together. Adjusting only one stop screw would distort the shape of the window and give you even more problems. To maintain the 4/32 window, we turn the lean and rich stop at the ratio of 2:1. So if we turn the lean stop a half turn, we should turn the rich stop a quarter turn. We also recommend that the lean stop screw not be turned more than a half turn, plus or minus, from the base setting made with the carb on the bench. Anything greater than this would require going back into the carb and adjusting the float, metering rods, and other things. But 1/2 turn should be more than sufficient. It's equal to about a 25% change in window position. To make the final adjustment, we need to have a thoroughly warm engine at normal operating temperature. Running the engine at 2,500 RPMs gives us a dwell reading like this. This is a lean command, meaning the car is delivering too much fuel to the engine. In our opinion, this is not acceptable. What we need to do in this instance is lean out the carburetor by turning both the lean and rich stop screws down at the ratio of 2:1. When the dwell is dialed in at 30 degrees, we return to idle and, using mixture screws, trim the idle mixture to achieve the 30 degrees dwell. If the 1/2 turn of the lean stop screw wasn't enough to achieve 30 degrees dwell at 2,500 RPM, this would indicate the carb is calibrated too rich from the factory. As a result, it would be necessary to change jets or metering rods in order to maintain 30 degrees dwell at 2,500 RPM and stay within a half turn of our bench setting on the lean stop. After the 30 degrees dwell has been achieved, it's time to move on to the final TPS adjustment. To make this adjustment, according to the book specs, we want the carb on the high step of the cam to read 0.52 hundredths of a volt on the meter. But as we've said before, plus or minus a hundredth of a volt is close enough. Once we do this, it's a good idea to use a silicone sealer in the hole to set the adjustment. The next thing we want to do is make a final map and baro check. To do this, we start the engine and run it until the timing is stabilized. We then unhook the vacuum hose from the map sensor and should see the timing retard. When we reconnect it, we should see the timing change back. Next, we add vacuum to the baro sensor, and the timing should also retard. If this happens, we know we have proper function in these sensors. Finally, we want to check the vehicle speed sensor. To maintain an accurate vehicle speed signal to the ECM, It's necessary to remove the speedometer head, clean the reflective blades with alcohol, then lubricate the speedometer cables. We recommend this procedure every 15,000 miles. Now, we're ready to put everything back together in preparation for the final road test. As we do this, we continue to look for any signs of possible malfunction. At this time, we also want to be sure to replace the rich and lean stop plugs. There are two important reasons for this. First, because the lean stop hole is outside the air cleaner, it must be plugged to keep the proper atmosphere in the car. Secondly, these plugs actually hold the adjustment screws in place so that they can't change position after we've set them. After replacing the rich and lean stop plugs, you start the engine and let it idle until it attains closed-loop operation. As you take your pincher off the purge valve, look to see if the duty cycle changes. If it does, it means the purge valve is leaking. If there's a change of more than 10 degrees dwell when you reinstall the PCV valve, this indicates excessive fuel in the oil and should be changed. When you're sure the EGR and canister purge are all reconnected, you're ready to road test. It pays to give the vehicle a thorough road test at highway speeds for at least 5 minutes. The last thing you need after doing so complete a diagnostic check is to have the customer come back with a complaint. That completes the video presentation of Computer Command Control. You are now better equipped than most to become a respected and profitable expert in computer control repairs. But the only way to truly master the 3C system is by doing it. So what are you waiting for? We wish you all the best of luck.